Okay, so can you see my PowerPoint?
Yeah.
Can you hear me?
Yeah, for those of us online, we are able to hear you and we are able to see your PowerPoint.
Okay, wonderful.
Professor Pan, can you hear me?
Yes, I can hear you. No problem.
Okay, thank you. I mean,
very clearly. So I mean, since the connection seems not so nice, so later on, I will switch off my video so that to make a better connection.
yeah, we cannot hear you very well.
Oh, really? So
Actually, those of us who are joining online, we are able to hear him clearly. Okay, maybe I'll come to the conference room. Just one moment, please.
yeah, I will and switch off my video. Hello, can you hear me now? Hello?
We can
Hello?
we can hear. Yes, we can hear you. Yes, we can hear you.
Okay, then I will just then leave my video closed so that yeah.
Okay, so maybe we can start now.
Okay.
Okay. Yeah. Okay, so so let me begin by apologizing for the delay. There were a few technical problems, but I think now they seem to have been solved. So okay, so let me welcome all of you to this very special event. This is a talk by Professor Pan Jian-Wei, and this is in celebration of the International Year of Quantum. And on behalf of all the members of the Center for Quantum Engineering Research and Education, TCG Crest, I would like to welcome you to this talk. And well, I'm sure that many of you know Professor Pan and his very important contributions to the field of quantum science and technology. But there are some young students who have recently entered the field. And so I think a few words of introduction is necessary. I will not take long. I'll just say a few words about his contributions. Professor Pan is a professor of physics and the director of the Center for Excellence in Quantum Information and Quantum Physics at the University of Science and Technology, China, in Hefei in China. And he's also the executive vice president of the same university. As many of you know, he's a pioneer in several areas of quantum science and technology, and his wide-ranging contributions have had a profound impact in advancing the field of quantum science and technology. In particular, his contributions in quantum communication, quantum computing, have made his group a world leader. And the prizes and awards that he has received are too numerous to mention. But I think I should mention at least one recognition that he has got. And this was in 2017. The Nature journal summed up his contribution and described him as, let's see, I mean, sorry for the interruption. I'll just repeat a few things again. The prizes and awards that Professor Pan has received are too numerous to mention. But I think there's one thing that I should say, which is that that his contributions have been best summed up by Nature Journal in 2017, and it described him as the father of quantum. And as we go along, as we make further advances in the field of quantum science and technology, it will become evident that the contributions of Professor Pan and his group are very seminal, and they will play an important role in advancing this field. So with these few words, I'd like to request Professor Pan to give his talk. Professor Pan.
Okay, so thank you. And thank you for your very kind introduction. And dear colleague and dear friends, and good and afternoon. So first of all, I would like to thank Professor Apanka Agawa for the kind invitation, and also for the alignment, which give me an opportunity to share my view and our progresses on quantum network through an online presentation, especially at this significant moment marking the 100th anniversary of the birth of quantum mechanics. So over the past century, quantum mechanics has become one of the pillars of modern science and has given birth to major modern technologies which fundamentally changed our lives. In particular, it was on the predictions of quantum mechanics that people invented semiconductors, lasers, and highly precision atomic clocks, which in turn led to the emergence of modern computer, as the internet and the satellite positioning system. It can be said that quantum mechanics has directly given birth to modern information technology. However, there are huge challenges in modern information technologies. As we all know, achieving secure information transfer is a dream of human beings since ancient time. For example, Sparta in 700 BC had already used a cipher tool named Cytel. Since the message is written upon the wound strip, it appears as eligible jump of a letter to anyone who does not bear a Cytel of the appropriate diameter. Around 400 BC, Julius Caesar in Roman Empire also invented a shift cipher to ensure secure information transfer. However, this ancient encryption method can actually be corrected by analyzing the frequency of the occurrence of letter. So historically, every advance in classical cryptography has been defeated by advance in cracking. During the Second World War, Alan Turing cracked the Enigma cipher machine, and moreover, in modern cryptography, such as the widely used public key encryption system, RSA 512, was cracked in 1999, and ISA 768 and was cracked in 2009. And now even ISA 1024 has been considered unsafe. Since all the classic inclusion methods that depend on computational complexity can be corrected in principle, it has been long suspected human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. So an everlasting question is, can we invent a cipher tool to ensure secure information transfer? On the other hand, and the demand for the computing power has been growing rapidly with social progress. In 1943, the chairman of IBM, Thomas Watson, thought that the world market may only need 5 computers, like Colossus. However, the computing power in the mobile phone today is already larger than the total computing power owned and used in the Apollo and the program. So nowadays, the world's data volume roughly grow 40% per year. So we are now in the so-called big data era. So there is an unprecedented demand for computational capacity in data analysis. However, the computing power now owned by humans is still very limited. So at present, the world's total computing power is insufficient to search for a target to the power of 90 bits within a year. So the major technological limit is the Moore's law that predicts the transistor density double every 18 months has come to an end. This is because the size of a transistor will soon reach the atomic scale, so that the electron tunnel effect will appear, and the circuit state of 0 and 1 cannot be well defined anymore. And meanwhile, another challenge in enhancing computational capacity is that the enormous energy consumption of artificial intelligence. For example, the solar generate a minute of video requiring 14,000 H100 GPUs to run for a month. The power consumption would be about 7 million kilowatt hour, which is equivalent to the carbon emission of a Boeing airplane 757 flying 7 million kilometers. Fortunately, quantum mechanics, after 1 century of development, come to the rescue for the problems confronted in the classical information technology. So before I explain to you some basic idea about quantum information, let me first make a brief introduction on the quantum superposition principle. As we all know, in our everyday life, a cat can only either be in alive or dead state. However, according to superposition principle, a cat in the quantum world can even be in the coherent superposition of alive and dead state. When we apply superposition principle to a multi-party system, we are led to the conception of quantum entanglement. For example, 2 cats in the quantum world can even be in the coherent superposition of alive and dead state. This implies if we perform measurement onto the first cat and is found to be alive, then the second cat will be instantaneously collapsed into the alive state, no matter how far away they are separated. Einstein referred to this phenomenon as quick action at a distance. Physically, any 2-level system can be used as a realization of a qubit. For example, we can explore the two-polarization state of a single photon to encode 1 bit of information. For a system consisting of 2 photons, they can be in one of the following 4 Bell state, the so-called maximally entangled state: horizontal, plus minus vertical, or horizontal, plus minus vertical. So for a maximally entangled photon pair, using the perfect correlation of the measurement outcome of photon A and B, one can precisely predict the measurement result on particle B according to the measurement result on particle A. Even the two particles are space-likely separated. Since Einstein believed the outcome of a measurement cannot depend on any action in space-like region, separate region, so he concluded that the outcome of a measurement is determined and prior to and independent of the measurement, which is a quite similar reasonable assumption of local realism. However, as a contrast, quantum mechanics predicts initially the initial set of 2 entangled particles are not identified. The measurement outcome on particle A will not only determine the value of particle A, but also the state of particle B immediately. This leads to quantum non-locality. So in 1935, Einstein, together with Podolsky and Lawson, published an interesting paper questioning the completeness of quantum mechanics due to a theory supporting quantum non-locality. Since both local reason and quantum mechanics can well explain the perfect correlation revealed by entangled state, at that time, one does not know how to experimentally test which theory or which conception is correct. Therefore, the argument remained at the philosophical level for about 30 years. So in 1964, John Bell proposed an experimentally testable inequality by constructing an observable from the measurement result of 2 particle entangled state. So if the measurement outcome on each individual particle are predetermined as asserted by Einstein's local reason, then the maximum value of this observable is 2. However, according to quantum mechanics, the measurement outcome on each individual particle are not identified initially, then the maximum value of the quantity can even reach 2 square root of 2. So since 1972, a lot of experiments has been performed to establish the violation of Bell inequality. And for example, in 1932, Friedman and John Clauser first observed violation of Bell inequality with polarization entangled photon pair from atomic casket. However, in this experiment, the 2 measurement sites are not space-likely separated. Therefore, via classical communication between the 2 sites, one can mimic the violation of Bell inequality even without invoking any quantum entanglement. So in 1982, Alan Ashpak and his colleague used a fast switch controlled by preset quasi-periodic signal to ensure the measurement process are space-likely separated, while failed to address the locality and detection loophole. So in 1998, Anton Jennings' group close the locality loophole using first switch controlled by random number generator. And in 2001, David Winland's group closed the detection loophole with entangled ion. So by 2015, 3 teams independently closed the locality and detection loophole. So all the former experiments well confirm the correctness of quantum mechanics, while still with some loophole, such as the freedom of choice loophole and the collapsed locality loophole that need to address it further. So the violation of Bell inequality implies the quantum world is intrinsically random. This is because for entangled state, before the measurement, even the God does not know what the measurement result will be. So an immediate application of quantum entanglement is device-independent quantum random number generation, by which true random number via violation of Bell inequality, even with the suspected device, can be achieved. So this scheme is secure against both classical and quantum adversary. So the first experimental realization was reported by us in 2018. So the device-independent quantum random number generator could find various applications in numerical modeling, artificial intelligence, and cryptography. Another important application of Bell theorem is entanglement-enabled secure communication as proposed by Arthur Eckhart in 1991. In the scheme, the perfect correlation of entanglement can be used to share secret key between Alice and Bob. So in the absence of eavesdropping, the entanglement will not be disturbed, so the maximum value of Bell inequality can reach 2 square root of 2. But if there is eavesdropping in between, so the value and then the unauthorized measurement will leave states of photon identified, so the value of Bell inequality can so the value of S cannot exceed 2. So in 2022, 3 independent teams demonstrate the device-independent QKD. However, in this experiment, as the key rate and the achieved secure distance are much limited, so it is still far away from a practical application. So interestingly, besides discovery in quantum foundation, from the test of quantum non-locality, physicists have developed groundbreaking technologies for coherent manipulation of quantum systems. This consequently leads to emerging quantum information science, including quantum communication and quantum computation. While quantum communication can ensure secure information exchange, and quantum computation can greatly enhance the computing power. So the quantum key distribution is the best known quantum communication protocol. For example, as one can explore the so-called BIP84 protocol to implement single photon based quantum key distribution. With the help of the shared secret key and the one-time pad encryption method, one can achieve unconditional secure communication. Also, QKD can provide and the fresh seed key for classical symmetric encryption with a much higher rate than classical method, which can substantially enhance the security of the existing communication system. And similarly, one can also explore the perfect correlation of entangled photon to perform entanglement-based device-independent QKD, as I just mentioned. Quantum teleportation is another interesting application of quantum communication, which is a way to transfer quantum state from one particle to another without actually sending the particle itself. This is very much like the way to achieve Star Trek in science fiction. Although nowadays it is far away from teleporting a person, it is visible to teleport various quantum states within a network, which is the essential ingredient for distributed quantum information processing. Interestingly, the state of one particle of an entangled pair can also be teleported. For two entangled pair, 4 and 1, 2 and 3. If one performs a barrel-state measurement on particle 1 and 2, as in the teleportation protocol, then the two remote particles 4 and 3 never interacted, can be entangled. This process is called entanglement swapping, which plays an essential role in long-distance quantum communication. So quantum computation uses qubit to encode information, which can be in a coherent superposition, and the information represented by them can be processed in parallel. Therefore, it can result in exponentially speed up in principle. One of the most famous quantum algorithms is Shor's factorized algorithm, by which one can efficiently factorize large number and break the public key encryption system. The superpower of quantum computation can also be used to greatly speed up, such as weather forecast, financial analysis, and drug design, and so on. So with the development of quantum information technology, it is foreseen to establish in future a large-scale quantum network or quantum internet to provide secure communication via quantum key distribution and provide an efficient way to connect quantum computer via teleportation and achieving an ultra-high resolution via quantum sensor. And moreover, we can use the quantum computer to achieve efficient information processing. So now I would like to mention some experimental demonstration. So the first proof of concept demonstration of QKD and the quantum teleportation were done in 92 and 97, respectively. We can see that the distances are quite shorter, both only about 30 centimeters. By 2005, several groups have demonstrated QKD over 100 kilometer fiber. However, it was later found out that due to the imperfection of realistic quantum device, mainly due to imperfect single photon source and imperfect single photon detector, there are serious security loopholes in previous experiments, making the secure distance of QKD in fiber was limited to the order of 10 kilometers. Then people might ask, then, I mean, the performance is so bad, so why we and would like to use quantum secure communication? So therefore, and there are two major challenges toward a large-scale secure quantum communication before we can finally promote any practical useful application. First, we need to overcome the secure loophole caused by imperfection of realistic quantum device. And second, we need to overcome the exponential photon loss in fiber to extend the distance of quantum communication. For example, and in order to achieve a quantum communication or quantum key distribution over 1,000 kilometer commercial fiber, and even with the perfect 10 gigahertz single photon source and ideal single photon detector, only 0.3 photon can be transmitted on average per century. So we have to overcome C2 loophole. So how to do that? So to solve the circular loophole caused by non-ideal single photon source in 2005, and the decoy state quantum key distribution was proposed. So in 2 years later, 2 independent teams, including us, and implement decoy state QKD over 100-kilometer fiber. So in 2013, following the scheme by Hao-Kwan Lu, and we demonstrate measurement device independent QKD, which is immune to any attack on detection, thanks to the ultra-precise frequency transfer technology recently, and the secure distance of MDI QKD has reached more than 500 kilometers in field fiber and more than 1,000 kilometers in coiled fiber. Therefore, as pointed out by Charles Burnett, in MDI QKD, Eve's untrusted device remain outside Alice and Bob's trust enclosure, so they need only trust themselves not to have inadvertently created a side channel to Eve through an incompetent design of their do-it-yourself light source. Therefore, with MDI QKD and the controllable DIY light source, information theoretically secure QKD with a realistic device can be approached properly. So how to extend the distance? One possible solution for large-scale quantum communication is a quantum repeater. So the central idea is to solve the problem of photon loss via entangled swapping, and to solve the problem of decoherence and via entangled purification, where entangled purification is the way to distill a subset of entangled state from a large set of less entangled state. So experimentally, it imposed 3 major requirements: and entangled swapping and entangled purification with high precision, and quantum memory with high performance. The first entangled swapping experiment was demonstrated 27 years ago in 1998, and late in 2003, and we implement a high precision fault-tolerant entangled swapping, and via visible entangled purification protocol with the help of linear optics in 2003, and we managed experimentally demonstrated the first high precision entangled purification. So the reason why and we need the quantum memory is because without quantum memory, the cost of the results in the multi-stage experiments of quantum repeater is proportional to 1 over p to the power 2n, where p is and the probability of emitting an entangled photon pair in each experimental run. Therefore, such a scheme is not a scalable one. However, if we know when the photon pair is created, and also we can find a way to store the pair on demand, then the total cost to implement entangled purification and entangled swapping is proportional to 1 over p squared. In this way, we can thus achieve efficient distribution of entanglement, of quantum entanglement between distant locations. So in 2001, and following the DLCZ single photon quantum repeater scheme, we managed, in 2001, and the DLCZ single photon basic quantum repeater scheme was proposed. However, in this scheme, and ultra high phase stability on the order of less than a few tenths nanometer after propagation of a distance few hundred kilometers is required. So such scheme at that time is very difficult to be realized experimentally. Therefore, in 2008, we experimentally relies on robust quantum repeater scheme, which was proposed by us in 2007, which only requires a stability on the order of a few 10 centimeters by making use of 2 laser cooled atomic ensemble, which are connected by a 300-meter fiber. So which is a demonstration of a building block of quantum repeater. So in order to enable a long distance quantum repeater, the storage time must be long enough to ensure every node to create an entangled pair, while the storage quantum state have to be converted into photon with a sufficient high efficiency to establish remote entanglement. However, in our 2008 experiment, as shown in this figure, so it's here at this point. So the lifetime is only about 1 microsecond, and the diffusion is only about 35%. This implies in order to, so the lifetime has to be improved by 8 orders of magnitude in order to fulfill the requirement of a 500-kilometer quantum repeater. So since then, many technological development have been carried out, including employing the clock state, which is insensitive to magnetic field, using a ring cavity to increase the true efficiency, and using a 3-dimensional optical lattices to suppress atomic collision-induced decoherence. In this way, 10 years ago, almost 10 years ago in 2016, and we managed to prolong the lifetime to near to a few hundred millisecond, and while with a near unity conversion efficiency. In principle, then the new coefficient already good enough support a quantum repeater at a distance of 500 kilometers. So to connect quantum memory node with a fiber, we also need to shift the atomic wavelength, because our quantum memory is atomic quantum memory, from 800 nanometer to a telecom and wavelength. Right. So with the developed frequency conversion technology, and in 2020, and we successfully managed to implement quantum entanglement between a quantum memory over large distance. Based on this, very recently, we managed to achieve a multi-node entanglement-based quantum network over a metropolitan area. Most recently, the entanglement distance of quantum memory between quantum memory has been extended to 400 kilobit in fiber, and the IYQ using entangled atom separated by 100 kilometer are also demonstrated. However, it might still need 10 more years before we can implement a practical quantum repeater. So you can see, since my first experiment in entangled swapping, we already spent 27 years to develop quantum repeater, but we still need another 10 more years. Therefore, almost 24 years ago, and we started to consider another promising solution for global scale quantum key distribution, which is through satellite in space. The satellite to the ground connection has significantly reduced the photon loss. This is because the effective thickness of atmosphere and for the vertical one is only about 10 kilometers of horizontal atmosphere. So almost 80% of the photon can penetrate the horizontal, can penetrate the vertical atmosphere, which means most of atom propagation in our space is in empty space with very small absorption and turbulence. So since 2007, we have spent decades in performing systematic ground test for satellite-based quantum communication. So in 2004, we performed the first ground test on distribution of quantum entanglement over 13 kilometers in Hebei City for the first time beyond the effective thickness of the allosphere. In 2011, and we demonstrated both entanglement distribution and quantum teleportation in Qinghai Lake over 100-kilometer free space, which verify the visibility of quantum communication via high loss, low orbital satellite to ground channel. In 2012, we performed direct and full-scale verification toward satellite to ground QKD under various simulated conditions of rapid motion and vibration and random movement of satellite, turbulence, and high channel loss. With all the development, after 14 years effort, so 9 years ago, the first quantum satellite missile was launched successfully. So with the missile satellite, we achieve a QKD between satellite and the ground station at a 1,000-kilometer scale. In the experiment, so the observed final key rate is about 100 kilohertz, which is almost 22 order of magnitude higher than using the fiber channel at the same distance. In the meantime, we also achieve satellite-based entanglement distribution and quantum teleportation over 1,000 kilometers. Later, using missile satellite as a trusted relay, intercontinental quantum key distribution between Beijing and Vienna over a distance of 7,600 kilometers has been realized. Meanwhile, we successfully implement QKD between missile satellite and ground and Calgary in Canada, and also with South Africa. So in future, we hope, and also we have some collaborate in India, we can jointly explore the visibility of global quantum communication. So along with quantum communication, many technology of coherently manipulating photons have been developed, such as high precision quantum interference of independent photon, phase stabilization, single photon detection, and frequency dissemination. All these together enabling optical information processing, also including optical quantum computation. So actually, by manipulating photons, we have demonstrated a small-scale quantum algorithm, but these demonstrations remain largely toys. For example, we can factorize 15 is equal to 5 times 3, and so on and so on. And so the remaining question is how to build a universal and large-scale quantum computer which can really beat classic computer. So given the huge technical challenge, as Freescale proposed, it will involve 3-stage goal toward the ultimate realization of a practical quantum computer. The first one is called quantum computational advantage, which means the speed up is so overwhelmingly huge that no classic computer can perform the same task in a reasonable amount of time and is unlikely overturned by classic algorithm or hardware improvement. So the second one is to construct some kind of quantum simulator to efficiently mimic the evolution of a complex quantum system. And at the same time, we also need to develop quantum error correction to overcome the inevitable quantum error to achieve large-scale manipulation of qubit. So with the quantum simulator, and we can study the mechanism of high TC superconducting and quantum material, and so on. Then the third and the final goal is to realize universal and programmable quantum computation with the help of quantum error correction. So quantum computation advantage is an important milestone in quantum computation by which one can show essential difference between classical and quantum physics. Just like using the Bell theorem to refute Einstein's local reason, establishing the quantum computation advantage by using entanglement as a valuable resource, one would reduce and refute the extended Church-Turing thesis, which states classical computer can simulate computational power of any physical process with polynomial overhead. So in 2019, Google first announced the quantum computation advantage with a 53 superconducting qubit processor named Sycamore. In this experiment, they generate millions of noise samples in 200 seconds, while they claim a classic computer would need 10,000 years. However, our recent study has shown with the latest tensor network algorithm, the same task can be completed actually on the classic computer only in 14 seconds. So therefore, the advantage announced in 2019 has been overturned. So it would be necessary to achieve some strong computation advantage. So in the superconducting quantum computing system, 18 months later, and we realized a 6063 qubit superconducting processor and realized a strong quantum computation advantage. So now, even compared to achieve the best classic algorithm, we still have advantage ratio up to 10 to 10,000 times. And very recently, and we already report 105 qubit Zhu number 3, which is estimated to have advantage ratio up to 15 order of magnitude compared to the best achieved classical algorithm. So in the parallel development in 2020, using photons, we realized Gaussian boson sampling machine 9张, showing strong quantum computation advantage. 9张 in the 9张number 1, we detect up to 76 photons, and its sampling rate is about 10 to the power 5 times faster than the classic computer with the nowadays optimal classic algorithm. So currently, the experiments on 9张number 4 has been complete, and the data analyzed is in progress. So the detected photon counts exceed 3,000, which is estimated to have advantage ratio about 41 order of magnitude. So besides the lovely progress in quantum computation advantage, and a universal fault-tolerant quantum computer is still far away. So fortunately, and quantum simulation may lead to important application in near term. Very recently, and we use bottom-up and approach to observe the first fraction of quantum Hall state using interacting photon. So, and we also, in this system, because the artificial system has the advantage of addressability, single-side control and readout, as well as programmability, providing a new avenue for experimental observation and manipulation. So finally, I would like to briefly mention our result in quantum simulation with arch-code atom. So compared to other quantum systems, arch-code atom have several specific advantages for quantum simulation. Since the interaction of atoms can be precisely controlled, thus various Hamiltonians can be implemented artificially. So in optical lattices, we have demonstrated the parallel generation of atomic entanglement of about 600 atom pair, and then and later more than 1,200 pair with high fidelity. With this system, we already demonstrate a toric code Hamiltonian and the anionic fractional statistics, which is essential for topological quantum error correction. And also, we managed to observe the so-called, quantum phase transition in the Fermi-Hubbard model. And the Fermi-Hubbard model is an important one to understand the high TC mechanism. So with several years effort, and we manage, we really observe the critical divergence of the spin structure factor and provide conclusive evidence of antiferromagnetic and ferromagnetic phase transition in a 3D fermionic Hubbard model. Okay. Finally, I would like to briefly mention our result in quantum error correction. So to achieve a fault-tolerant quantum computer, quantum error correction is needed. However, the threshold for tolerable error rate of a traditional quantum error correction is remarkably low, which is about 10 to minus 5, which is extremely hard to implement within the current technology. So a possible solution is to perform error correction. So, several leading and quantum computing and computational groups are engaged in the experimental realization of service code. In 2002, two independent groups, including us, report the first repeatable error correction code on D equal to 3 in 2022. Then 1 year later, Google's Sycamore experiment report the service code with a code distance D equal to 3 and D equal to 5. In the end of 2004, Google's Willow showed exponential logic error suppression with D equal to 3, 5, 7. So most recently, we are working on error correction experiments for D equal to 7, 9, and 11. So, with the help of quantum error correction, and it's foreseen, it's possible to implement a universal quantum computer within next 10 to 15 years. So before concluding my talk, I would like to mention some future prospects. So in the future, it's foreseen to establish a global quantum communication network, quantum network, and by combining metropolitan quantum communication network and intercity quantum communication network connected by quantum repeater and long-distance quantum communication with quantum satellite. So for quantum repeater, in about 10 years, is expected to support quantum communication at a distance of a few thousand kilometers. As to satellite-based quantum communication, there are still several technological challenges need to be overcome. So, and the solution is to form a quantum constellation with multi-lower satellite to build a more efficient network, and the GEO quantum satellite with a much experimental time. To do so, a prerequirement is to ensure that satellite work in solar radiation background. So in 2017, we have realized long-distance free space quantum key distribution in daylight. And very recently, we managed to launch a satellite named Jian-Wei, and which has a much lower payload compared to the missiles. So the Jian-Wei #1, we only have a payload of 20 kilograms, while the missile has 250. And also for the cost of the ground station, in the first time the weight is 13 tons, now already less than 100 kilograms. So, so the QKD between microsatellite and portable ground station has been implemented. So the first GEO quantum satellite is currently under development, which is scheduled to be launched in the middle of 2027. Moreover, the large-scale quantum communication network also provides a new platform for the study of quantum metrology. And with the GEO satellite, we also plan to implement intent distribution on the global scale. It's about 10,000 kilometers. Then with the help of global intent distribution, one can intend multi-atom in remote atomic clock. In this way, we can dramatically improve the short-term instability of the atomic clock. So on the other hand, and leverage the ultra-precision optic atomic clock developed by our colleague and the optical frequency transfer technology and so on, we can achieve precise timing and frequency transfer dissemination with long-term instability by 4 orders of magnitude better than the previous one. So therefore, our GEO satellite will carry on an optical clock with a fractional instability 10 to minus 19, enable the comparison of optical clock among China, Europe, and South Africa. This will demonstrate the visibility of a global precise time information sharing and lay the foundation for a redefinition of the time unit second. Right. Okay. Yeah, so I just conclude. Moreover, in outer space, the magnetic and gravitational noise are negligible, so the fractional instability of atomic clock may even reach 10 to minus 21. So with ultra-precise time information sharing network and the long-base time interferometer, we can also explore the quantum communication and quantum metrology to provide new proofs for fundamental physics, such as detection of gravitational wave and hunting dark matter and so on. So in the field of quantum computation and simulation, our next 5 years effort is to realize coherent manipulation of a few hundred or up to a few thousand qubits for studying the mechanism of high temperature superconducting and quantum Hall effect and so on. So in the next 10 to 15 years, with the help of quantum error correction, it might be possible to achieve coherent manipulation of millions of qubits to lay the foundation for universal quantum computation. Thank you for your attention.
Hello. So we would like to thank Professor Pan for very illuminating and very comprehensive talk. And I think now floor is open for questions. So I think, are there any questions online? Can we?
Yes.
Just a minute. Oh, okay.
Okay.
Yeah, so just 1 minute. So we are just asking our online audience if they would like to ask questions. There is something in chat. Yeah. Okay, so one question is how you have mitigated the disturbance due to vibration caused in orbit satellite to ground, station, this QKD misses. Okay, question is a little, okay.
Sorry,
Okay.
I cannot hear very clearly. So could
Sure,
you
sure.
please repeat the question, or I would like to see where I can see the question.
I think in the chat they are there.
Okay. 你帮我看一下。他们有些问题是在。 Okay. So how you have mitigated the distribution due to the vibration causing orbital to ground QKD? Yes. So we have some adaptive optics. So we use some feedback because the turbulence caused by the airflow and the change, on the order of millisecond level. So as long as your feed forward is fast enough, then you can well compensate the and the light and front with the help of adaptive optics. Yeah. And
Okay.
this is the first question. So what is the scope using photonic chip based QKD for
clear.
Okay.
Uh,
Yeah.
Yeah, okay, we can go to this question. How did you reduce the weight of the satellite, this new satellite?
So now our light source is very small. It's all integrated on a small chip. But of course, our optical terminal is still quite big. We need something like a 20 to 30 centimeter telescope to send our single photon light.
Okay.
Yeah.
Yeah.
So the third one is
From
Okay, so for the next question, we can look at.
research organization.
Okay, nowadays.
Okay. So right. So for the practical and quantum repeater, right? So for the time being, and we concentrate on the development of quantum repeater and with fiber. So very recent, as I just mentioned, we already managed to achieve deterministic entanglement distribution over 100 kilometers. So we have an ambitious plan. We want to implement maybe within 5 years, to achieve determined entanglement distribution in fiber over 1,000 kilometers. Yeah. So then and actually, if we can have a space-based quantum memory, then even make the realization of quantum repeater much more easier because the photon loss in space is much smaller. So then if we can have some tool and memory in the ground, then we send the 2 single photons to space. Then we perform the Bell measurement in space. So in this way, the quantum repeater will be much more efficient. So for the time being, we only develop 5 basic quantum repeater. But in the future, we also want to pursue the possibility to combine the advantage of fiber and satellite. Yeah.
So thank you. So I think we can take.
Okay, how to reduce the weight of the satellite of Jinan number 1? So the main idea is we have a much more compact payload. Yeah. So that first of all, we have much better compact setup so that the payload is significantly reduced. In the meantime, and we also significantly reduce the diameter of our telescope. And because originally the telescope in the misuse is about it's about something like 30 or 50 centimeters, but now it's about 20 centimeters. Yeah, but in order to and while with smaller diameter, then the beam divergence will large. So we really need to develop a very nice technology to make our beam angle is close to the deflection limit. So in these 2 ways, and we managed to reduce the weight of the satellite, especially as a payload. Yes. So my question is, when we are talking, do they have end of end, or are we using trust node for that? Yes. So for the time being, because we only managed to do quantum key distribution between the satellite and the ground station. And if we only use single photon technology. So in this sense, and the satellite is our trusted node. So we only have one trusted node, is a satellite. If the satellite is under your control, then you can believe the quantum key distribution. But as just mentioned, in the future, we want to perform in-time distribution on the order of 10,000 kilometers. Then in this case, and even the satellite is controlled by your enemy. Why you have the violation of Bell inequality? You know the key between Alice and Bob are still safe. So in this way, and the satellite is not necessarily to be a trusted one. So that's our next step. So in 2027, we will try to achieve, to implement in-time distribution over 10,000 kilometers. Yeah. So the MDI QKD and the twin field QKD. Actually, twin field QKD is an efficient version of MDI QKD. So the original MDI QKD, we use two photon interference. Yeah. So for the twin field QKD, we use single photon interference MDI QKD. But the problem is for the two photon MDI QKD, we do not need a long distance phase stabilization. So the land stability is only need to be on the order of a few 10 centimeters. But for the twin field QKD, we need a much better phase stabilization. So in this sense, we would need the phase stabilization technology. Yeah. So that's the main and difference.
Okay, so one interesting question is what are your plans for satellite relay? Do you plan to create a relay with many satellites or only a few?
Yeah. So in future, and as I just mentioned, next year, and we are going to launch 4 microsatellites to form a quantum constellation. Yeah. So in this sense, I mean, we plan to create a relay with many satellites. Yeah.
Okay, so I think I mean, in audience, and will they like to ask some questions directly? Also, I think this issue of what can they respond? No. Can they ask question directly?
Yeah, hello.
Okay.
Yeah, am I audible? Hello.
Hello.
Yeah.
Yeah, this is Uttam from ISRO, Indian Space Research Organization. Actually, you told that microsatellite which you have developed with overall weight of around 20 kg. So you told that it is based on the integrated photonics kind of setup. In that case, when we compare with respect to the bulk optics based satellite, which I think for Mises it was done with bulk optics. So with respect to that, the drive electronics which is required for driving these PIC chips will add a huge amount or maybe a higher amount of weight than the bulk optic based QKD. So how did you manage the weight of the extra driving electronics which is required for driving the chips and for conducting QKD?
Yeah. I'm sorry. I really cannot hear very clearly because it's lots of noisy. I did not get your question due to the bad connection. Maybe.
Yeah, I think well, that's not very
I will type the message. Maybe you can answer to that
okay.
in the
So
chat.
okay. So
What is the? Yeah. So probably you can just send me the message. I can see the message much better.
Hello, Professor Pan.
So in the UD question is
Sure,
by
sure.
Atam Day. Okay, right?
yeah, So question, can you see what is the question chat? So I think in chat, I think Uttam Day has put some question. So let me. Okay, so what he is asking is a device electronic which may be required for driving PIC chips in case of microsatellite increases the weight compared to bulk optics based QKD. How did you manage the weight?
So means drive electronics, which may be required for driving PIC chip in case of microsatellite, increase the weight compared to the bulk optics basic QKD. And is this your question?
Yeah.
Okay, so I really do not know too much about details. I mean, so then I need to ask my colleague because and which will not develop is not directly developed by me. Yeah. Sorry, I do not know too much details about your question. Yeah.
So I think Sumit wanted to ask some question. Sumit, are you wanting to ask some question?
Yeah.
Hello, Professor Pan. I asked you the question about the relay. So what do you think, how would the global scale quantum communication would be feasible with or without the relay? So, and what kind of relay are you thinking about in the future? I work.
And without the relay, and you mean, okay. I think for the near term, it will be difficult. I mean, at least we need to believe the satellite. I mean, because for the and because we have two type of QKD, right? One is single photon based QKD. So in this case, anyway, we need to believe the satellite.
Yes.
Yeah. So satellite will be anyway will be relay. Okay, that's the first thing. Then the second thing is, as I just mentioned, we should be able to implement and entanglement-based QKD over 10,000 kilometers. But in this case, the key rate is very low. And you know, it's probably only a few, that means key per second. So it's of no practical application. But for the related basis, so the key rate can be much more higher, could up to 1 million or few million, I mean, key per second. So in the shorter term, I think it will be difficult for us to avoid the relay. Okay, and that's one thing. Then the second thing is, and if we manage to do, and for example, something similar to the free space-based twin beam, twin field QKD, then I mean it might be possible without using the satellite as a relay. So I mean, but for the time being, for the phase stabilization over 10,000 kilometers and is still very technically challenged. So in our plan, we will first achieve high precision timing dissemination. And as long as this is succeed, then it might be possible to perform twin field based QKD. Then we don't need to have relay. Okay, that's the space solution. But with the fiber solution, without space, okay, without satellite, even within the next 10 years, I think we can extend to 10 kilometers, no, 1,000 kilometers, which already very good result. Yeah. So that's still in the basic research area. Yeah.
Thank you for the answer. I was not talking about the trusted relay though. I was talking about the untrusted relay where you can reflect the light from satellite and use the satellite as a relay. So are you thinking of that kind of a relay, like you send light from a medium to high orbit satellite and then reflect it off an LEO satellite or something like that, where the satellite is not a trusted relay?
So it means, yeah, sure. I mean, the combination between LEO satellite, low orbit satellite, and high geostationary satellite, the combination is always good. Yeah.
Okay, we actually worked on a relay paper like this, where yes, LEO satellites are considered like lenses to focus the light, and later on there are more work in that in ground called vacuum beam guides
Okay.
and things like that.
Mhm.
So I was
Ah.
just interested to know if you are also doing this relay with reflection or something like that, where you
Ah.
can do untrusted quantum communication for too long distances.
Yeah, not for the time being. Yeah, we do not have such a plan. Okay,
Thank you. Thank
but
you.
it's wonderful. So I would like to mention we are very open for international collaboration. So if we are interested, I mean, because anyway, next year we are going to launch 4 more microsatellites. So we have enough resource for some collaboration. Yeah.
Thank you very much.
Okay, are there any more questions? No. Okay. So I mean, Professor, I mean, as you were saying, being able to manipulate millions of qubits by a quantum computer, say maybe 15 years down the road. So I mean, do you think this RSA crypto system can be broken, say, in next 15 years by a quantum computer?
Now, I mean, for the quantum computer research, basically we concentrate on vaccine in China. So we have a very complete team. And for example, I mean, you know, we have one topic is topological quantum computing, right? Which is the so-called Majorana fermion and so on, but it's still a long way to go because now our colleague did not even achieve a single topological qubit. Yeah, but we have some colleagues work on this. And also we have another 3 main focus. One is superconducting quantum computation. As you know from our publication, I mean, so the Google will be our main competitor. So we are really focused on this very much. Then the second one is neutral atom, which now is a hot topic. So recently, I mean, we also have some nice result, I mean, from our colleague. And the third one is ion trap quantum computation. And we also have several, I mean, very nice team and in China. Yeah, so these are 3 main focus. But for the photonic quantum computation stuff, we are focused on 2 new approach. So the first one, we want to investigate the possibility to achieve strong nonlinear coupling between individual photons. So if this can be successful, then actually photonic quantum computation might be even better than all the other candidates. Due to such a system has no interaction with environment and also, I mean, can work at a room temperature. And moreover, so in photonic systems, the main error is caused by photon loss, right? So I mean, for the error correction code for photon loss is much simpler than the other quantum error correction code. Then if this could be successful, then we might have a bright future for photonic quantum computation as well. So we now try various things. Yeah. Yeah.
Okay, yeah, so just one more question.
Okay, thank you for an excellent talk. I have seen your papers on calculation of ground states of molecules, quantum chemistry calculations using VQE. Are you thinking of doing more calculations on electronic structure of molecules using fault tolerant quantum algorithms? Yeah.
Right. And this is, I mean, one of our and major effort. Because now, I mean, all the calculation still can be done and with the classical supercomputer. But now we have a project which combine AI, artificial intelligence, and the quantum computation. So the quantum computation could be and preliminarily estimate for the ground wave function, for the ground state, yeah, for the ground state wave function. So as long as you have a better estimation of the ground state wave function, then combine with transformer ChatGPT, and you can be much more efficient. So which is kind of combination in future to calculate the quantum chemistry. That's the one thing we are going to do in the near future. We will pay more attention to this project. Yeah.
Okay, thank you very much.
Okay, are there any more questions? Okay, in case that there are no more questions, I think we are very grateful to Professor Pan for taking time from his very busy schedule to educate us about the past, present, and future of quantum network, as well as whatever is happening in quantum computation also in his group. I think we have all benefited a lot from his talk. So we are grateful, and we would like to thank you, Professor Pan, for this delightful talk. Thank you very much.
Thank you for your time, and thank you for your invitation. Bye-bye.
No, yeah. Thank you. Okay, my friend.